Hello, everyone. Welcome. The final presentation before lunch. So everyone can get lunch after this. It'll be great. So, as the world is adopting more mobile devices, we're writing applications that need to be used on different devices. So for example, your application might have like a server side. It might also have like, you use the Android version. You might use the Android version of your app on 2 Android devices. Your users might use your app on an Android device and on the web. So you have like the application may have its data sort of distributed through different things. So basically, you often will have this situation where you have some data on your server, that's your application data, but your client will also have some of that data cached somewhere, maybe on the web, maybe on Android, depending on how you're doing it. And sometimes you have this issue where people are editing this data. So maybe you have a document open on 2 different devices. Someone edits that, but they're offline. And then someone edits their device here, and then that data gets saved, but then there's this offline data, and they change the same thing, but in different ways. So you have this problem where it's like, how do I reconcile these 2 different copies of the same data? And this problem is actually a very difficult problem, if you've ever encountered it. Has anyone encountered this problem before? Some people, yes, cool. Yeah, so this happens a lot, actually. You've got data saved somewhere else. You need to reconcile them. So I am Matt Gillingham. I am an engineering manager at Mercari. And this presentation is conflict-free replicated data types. So in terms of keeping data synchronized across devices, you've probably already seen different approaches to doing this. Probably the simplest solution that many organizations use in practice is called having a single source of truth. So in a lot of cases, what happens here is maybe you have a back end that's written, and you have your clients have a front end, and that has an API. So basically like, okay, I edit something on my client, I send that data to the API, and then the back end deals that, and then they store that information in a database. And in the most common case, that database sort of acts as your single source of truth. So whatever is in the database is the data. If somehow your application on the device is out of sync with that data, like is it cached, was stale, or something like that, then the single authoritative version of that data is whatever the database happens to have. So in this case, you sort of solve the problem of having conflicts by saying like there is an authoritative copy, and that copy is the data, and anything else, if it's in conflict with that, it loses. The thing that's in the database is the real thing. That type of solution is one solution to this problem. It's actually the easiest solution, and it's probably the solution that you should use unless you have a good reason not to. But you might also have seen some other forms of conflict resolution in your work as developers. So one example is Git. Who here is using Git? It's very popular, probably a lot of people. And have you ever had to handle a merge conflict? So really, like in Git, Git is actually kind of distributed. Probably most of you are using like GitHub or something as your single source of truth in one sense, but that's not actually how Git is designed. Git is designed as a distributed system. You can actually have like multiple servers that you're sending code back and forth in. It's actually a distributed model. And when you have data that like somebody edited this source file, somebody edited this source file in a different way, there's an algorithm that tries to work out how they should be combined, but sometimes it can't do that, and it gives up, and it gives you a merge conflict. And so basically, this is a way of saying that, well, I don't know how to solve this, so I'm going to let the user decide which copy of this data or how this change needs to be reconciled. So this is a second approach when you have conflicts, is essentially to sort of give up and ask the user to figure out which version of it they really want. And then you may have also used Google Docs. Does anyone use Google Docs? Okay. So in Google Docs, like you can have 2 copies of a word processor open at the same time and edit some text, and you see that text come there, and people are typing in the same document, and it somehow very quickly manages to incorporate both of those changes, and that's pretty interesting. So basically, if you look at the implementation of Google Docs, it's using a technique called operational transformation, which is one potential solution to this problem. Essentially, operational transformation is a technique where you sort of if someone edits something, you have this thing up here that figures out what those two changes are and actually manipulates the operations and sends them to the other side. It's interesting, and if you want to look at it, it's a fascinating topic, but it is pretty complicated to implement. And also, this is a solution where if you're using it, you're probably, or let me put it this way, you need to have a specific server-side implementation in order to do this. So you're probably designing your whole system up front around this problem of you want to have a collaborative editing environment. And that's the case when you might want to look at a solution like operational transformation. So the thing that I'm going to talk about is conflict-free replicated data types, which are another way of solving this problem that have some interesting benefits. The first is that compared with something like operational transformation, they're actually pretty easy to understand. I'm going to go through some really simple examples of how to do that. And another thing that's nice about them is you can actually build from the simple ways of doing things to get more complicated behaviors, which is mostly what this talk is going to be about. The other thing that's interesting about them is that they're solved at the data model layer. So it actually doesn't really matter what your server-side implementation is like. It's basically just particular data structures. If you use these data structures with the, the APIs that are accessible to them, then your data will be able to synchronize without conflicts. So it's really simple in that way. And also, it does that without needing to prompt the user or something. So in this talk, my goal is to give you an intuitive understanding of what CRDTs are so that you can see what they are and how they might be useful in your application. I'm not going to show you any code, but I hope that after this talk, you would be able to start writing simple examples on your own based on the understanding that you'll gain. Or maybe you can use a library and know what it's talking about. So in order to get started, I'm going to walk us through a couple of very simple conflict-free replicated data types. The first one is called a grow-only counter. So imagine that we have 3 different devices. There's an action that these devices they can do. They can send an increment command. And our goal here is that all of these devices, different ones, they can increment things at different times, but at the end of the day, we want them all to have the same value. So basically, it looks like this. So here's our 3 devices. We can see the top one and the bottom one, kind of independently of each other, both increment the counter. And then the other thing that they do is they broadcast that increment operation to the other devices. So the top one there increments, and then this one receives that and increments, and this one receives and increments. I should mention they all start at 0 there. So that one sends an increment command, updates its value to 1, tells the other devices, OK, increment to 1. This one does an increment, does its own command, tells the other ones to increment, and here gets the 2. So we basically see each one of these commands, each one of these, or the system has 3 increment commands. And among the things I want us to observe in this is that we have this increment command and they're broadcast to the other ones. They receive these commands in different orders. So this one goes blue, green, orange. This one goes blue, orange, green. This one goes orange, blue, green. But at the end of the day, as long as all these devices receive all 3 of those commands, they're all going to have the number 3 at the end. Even though at various times they don't, like this one is 3 before that one even becomes 2. But as long as at the end all of the increment operations are broadcast throughout the network and they all receive them, we can be pretty sure that they're all going to end up as 3, as long as there's just 3 increment commands that are fired. So just to reiterate what I just said, in this model, each one of these receive those commands in different order. They do not, in time, have the same values. but at the end they do. And that's what we care about. At the end, when all of the operations are there, will they all have the same values in the mathematical sense? The next example I want to talk about is called an add-only set. So it's similar to what we just did. We're going to have 3 devices. Each one has the ability to insert integer values into a set. And these are sets, so we're not going to allow duplicate values, although actually it wouldn't matter if we did. But these are just sets. They are unordered, and they have integers that they hold. So basically, the way that this one works is each device starts out with an empty set. Then whenever it inserts a value, it puts it in its own set, and then it sends its set to the other devices. And then when the device receives it, it sets its own local copy of the set to the union of the set that it currently holds and the one that it's received. So this is what it looks like in practice. All the devices start off with the empty set. We insert 1. So this one inserts 1. At the same time, roughly, the other one inserts a 2. And then when this one inserts a 1, it sends the set containing 1 to the other devices. The other devices take that and make their own internal set, the union of what they just received and what they're holding. And if we look at these examples, we'll find, again, it doesn't really matter when any of these devices receive that update. As long as they receive that update, at the end, they're all going to end up with the same values in them. Again, reiterating what I just said, the sets are not always the same at all times. This one at one point is just 2. That one is like at one point, 1, 3. Well, that one's 1, 2, 3. They all have different values for a while, but in the long run, they all end up with the same values. So there's a property now that we're talking about, which describes sort of what I've been indicating, and this is called strong eventual consistency. Strong eventual consistency means that a distributed system, which is basically a system that lives on multiple devices at the same time, is guaranteed to have all of its data converge to the same value if all of the updates are made. If you're interested in the mathematical term for this, and you want to Google this later because this seems like an interesting topic, you should memorize this term, which is called a monatomic semilattice. This is basically the mathematically equivalent term for what I'm describing. In the field of math, they call it this. In computer science, we're calling them conflict-free replicated data types. Yes, take a photo of that slide. Strong eventual consistency does not mean that all of the devices will always end up with the same data in the real world. For example, your device in the real world might run out of batteries. It might break. It might get disconnected from the network. If it does not receive all the updates, it will not end up with the same values as the other devices. So we can see an example of this here, right? So at some point, something happens to the middle device. I don't know, it fell down and was broken into 1,000 pieces. So at some point, it stopped receiving those updates. So at its last point, this is what it has. It does not eventually have the same data. But in the real world, that's how these types of systems actually work. There's not that much you can do about it. If you know how to have all of your devices get the same data without even be connected to the network or working, then please talk to me after. I'm really interested in how that would work. In general, though, we think this is like a real-world constraint of just working in computers in general. We have to accept that sometimes things don't go well. So the property that we're interested in is, given the assumption that everything does go well, we have something that is going to allow us to all have the same values. So each of the devices is going to have to receive all of the updates for this to work. But if it does, it will work. There's a second point I want to make about conflict-free replicated data types. It's kind of a small issue, but it has to do with sort of how they're implemented. in the two examples that I gave, the counter example or the set example, we actually have already seen two approaches. In the first approach, we had a counter which sent an action, an increment action to all of the devices. And when the other devices received that action, they did something to their data. And this is called, this is about dealing with an operation then. So it's communicating an update operation to other devices. In the set example, it didn't send an operation, it actually sent the entire set. So it sent whatever the current data that it has to the other devices, and those devices did a merge. And the key point there is that the merge operation can happen in any order, and you will still receive the same end result. So it's important to point out then that there's actually two ways of doing this. Although you can demonstrate, which I'm not going to do for this talk, that they can be interchangeable, they can be converted among one another. But it's worth noting that there's these two different approaches if you want to build one of these types of sets. So the first type is actually called a communicative replicated data type. And what you're actually transmitting is the update operation. There's one important thing to realize about this. Usually with conflict-free replicated data types, you don't have to worry so much about your network. It's one of the nice points. It's just data structures and merging them, and you don't necessarily have to care how the data is passed. But if you're implementing an operation-based one, you have to realize that if you're in a networking environment where the same message might be sent more than once, it won't work. Like if one device just said like, okay, I'm going to send an increment, but your network was such that it delivered that message twice, it's not going to work. The increment would be sent 2 times or something, and then you'll end up with different values. So if you implement a communicative one, it does matter a little bit about the nature of the network environment that you're in. For a convergent replicated data type, they just send their entire state. So you take whatever you've got, send it to the other device merges that with whatever it has. And again, the thing that's important is that regardless of the order of the merge operations, in the end, you'll end up with the same value. So I've shown you some examples of very simple conflict-free replicated data types. I'd like to first of all start with an example of trying to build something that's distributed that does not work. And from that, I'm going to show you how you can turn it into something which will be able to do this. And then that will also allow us to see some of the more advanced techniques that are used when dealing with conflict-free replicated data types. So let's start with a set. So before I showed you a set where you could only add items to. But now let's have a set where you can also remove items. Okay, so here we have a problem. So the insert operation, so let's say that both the top and the bottom, around the same time, they put 1 into this set, and they send that to the other devices. So here we see, like, okay, at this stage, everything is fine. This one inserted 1, it received a 1, it already has 1 in it, so it doesn't do anything here. It's just like, okay, well, you told me to insert 1, but I already have 1, so nothing happens. Same thing happens there and there. But now, the key thing is this insert operation never made it to the second device. Now we have a remove operation. So this one's like, okay, I have this 1, but I don't want it anymore, and it removes it, and it tells the other devices to remove their 1s. So now everything is empty, except because this insert never made it to here until after this. At this point, it receives the insert, and it's like, oh, okay, I don't have a 1, so I'm going to put the 1 inside here. And now, in the end, in this system, you have 2 devices that have an empty set, and you have 1 device that has a 1 in it. So one of the important things to recognize is I've shown you 2 successful cases, but actually you can't just design this with any data structures. It really does depend on the nature of the information you're working with. These sets with this system are not guaranteed to arrive at the same values. And a lot of the reason is it depends on the timing or the ordering in which the operations are received. So we're going to fix this. And by fixing this, I'm going to show you how you can design a little bit of a more complicated system. And usually we do that by combining conflict-free replicated data types together. So one thing about them is that if you use some strategy where you use multiple ones in the same system, you can still have a system that is guaranteed to converge just by building on sort of more fundamental components. We've already seen that having add-only sets do converge over time. So why don't we create a system where we have two sets, one of which is the items that we're going to add, and then we'll have a second set that's the items that we're going to remove. It's an add-only set of things you're going to remove. That's a little complicated, but hopefully the idea makes sense. And then we're going to say, like, OK, there's a final set, which will basically be the items that we added, and then we take out the items that we removed. So what does this look like? So here, all the devices start with two groups of empty sets. So the top one is where we put things that we want to insert, and the bottom one is where we put things that we want to remove. So here, we inserted one. In both these cases, we inserted a 1. So everything in their insert set has a 1. Here, when we remove something, we put it down here into this other set. And so we can see that this comes really late, just like it did before. But what happens here is the 1 is in the insert set and is already there. The remove was just added to the remove set. So at the end, we end up with two sets. These are all the things we've inserted. These are all the things that this system has ever removed. And then we just take out the ones that we've removed from the ones we've inserted, and all of them end up empty again. So in this case, we can see by combining two add-only sets together, we're able to create a system that will end up with the same value after all the updates are received. And again, that's repeating. We can create, so now we've created a system where we can add and remove items. You might say, like, that's interesting, but what if in the application that I'm building, I want to add an item, remove an item, and then I want to be able to add that item back? In the system that we just built, actually, if you think about it, that's not going to work. These are all the items we've ever added. These are all the items we've ever removed at any point in time. So you can't add something, remove it, and then add it back, because it'll still be in this remove set, and we'll take it out at the end. So that's not going to work if your application needs to do that, which is a pretty practical thing, and probably a lot of applications want that. So we've already seen that we have this approach where we can take two conflict-free replicated data types and combine their behavior. What if we do this with another one that we've already studied, which is the counter? So now I'm going to introduce, and this is the most complicated example, so try to just follow me through here. This is something called a last write wins set. And so we're going to use this counter to sort of create the concept of time in our system. So what I mean by that is, I don't mean time in the sense of like the physical clock on the device. We could try to use that. We could try to say, like, OK, we're going to update this set, and we'll include a timestamp of the current system time. But the reason why it's not a good idea to do that is that, for example, users can change their system times. They're not always in sync with one another. I mean, imagine if we were to do last write win set, and their user could like set their clock one day in the future, then all of their edits would win and everybody else's would lose. So basically, we don't want to use the system time, but we still do want to have a concept of time in our system that enables us to decide, like, what order did these events occur in. So what we're going to do is just have a simple integer counter that counts up, just like we already saw in our counter example. And just having a counter matched with the operation will allow us to create a kind of ordering that we can say, like, one of these events occurred after another event. And if you're interested in this term and want to Google something else that's interesting, this is called a Lamport timestamp. Yes, good. At least one person's taking a photo of that slide. So this is how this system is going to work. The device that creates an operation, so either an add or remove, it's going to increment its internal timestamp by 1, and it's going to send that timestamp with the operation. The other thing that I want to point out in this system that might be a little confusing is the timestamp is actually internal to the system. It's not sending its own timestamp. It's marking the operation with a timestamp, but its own counter is never sent to the other devices. And the device that receives an update is going to look at the timestamps that it has, and it's going to update its own internal timestamp to be the highest value of what it has received plus 1. And also, if it receives an event that's like has a timestamp of 3 and its internal timestamp is already like 20, it's not going to update its timestamp. It's just going to, well, probably do nothing. But it doesn't update its count. If its timestamp is already past what the operation it received is marked at, it doesn't change its own timestamp. So the values of the timestamps themselves don't necessarily converge. But remember, they're internal. That doesn't matter so much. So the timestamps might end up being different in the end, but they're just internal to the process. The set that they are creating will converge. And then after we've received these sets with these timestamps of operations, we'll use those timestamps in order to determine if an insert or a remove happens. And this is the format of the set that we're going to send. So basically what I'm saying here is I'm going to add an element to this set. It's going to have a timestamp of the last time that something was inserted in this system, and it has a timestamp for the last time something was removed in the system, and it's passing that collection of values together. As I said, this is the most complicated example in here, so sorry if that's a lot to follow. But hopefully the concept at least is somewhat intuitive. So what we do is we have all these devices start out with just an empty set and a counter that's 0. When it inserts an operation, it inserts 3 things. What got inserted, in this case an A, the first thing, which is the current timestamp, which is 1, and I'm using -1 here to represent that nothing has been removed. There is no remove action that's been performed yet. So it inserts those 3 values and sends those values to the other events in the system. This one is sending basically the exact same message, so it has no impact. But the other thing to realize is when something receives it, its internal timestamp becomes the highest value that it has yet seen plus 1. So we can see in the first step, everybody inserts A with the value of 1. Now here is where things get interesting. So the bottom device wants to remove that A that's been inside of there. So it generates a remove operation. Its current timestamp, it increments its timestamp. Every time it does an operation, it increments its own timestamp. So its timestamp was 2. So then it updates its timestamp to 3. It puts that 3 here and says, I'm removing something at time 3. And then it broadcasts that. See, up there we see that the top device says, oh, I'm receiving something with a timestamp of 3. I'm going to go ahead and update my internal counter to 3 plus 1, 4. And then this one up here is like, I want to insert that A back into the set. So it increments its counter by 1, 5, adds an insert operation of A and timestamps and updates the timestamp. It already has an A, so all it really does here is update the timestamp of A and say, now I'm inserting A at 5. And if we follow this through the system, we'll find out that all of these end up with a set of values that have A, 2 timestamps. It was inserted at 5 and it was removed at 3. So it's going to look at that and say, this is a last write wins set. So it's going to look at which one of these has the highest timestamp. Well, the insert does, so I guess there is an A in this set, and we end up with an A. So using this approach, we can both add and remove items from the set multiple times. So just a summary of what we've seen so far. The key point to take away from this is, especially if you're interested in problems of conflict resolution, if you organize and collect data in particular ways, we can create situations where the data structure itself can prevent conflicts. Also, simple conflict-free replicated data types can be combined to create more powerful and complex examples that can do stuff. We started out and we could just add things, but we ended up where we can now add and remove things multiple times and everything still converges. So by combining simpler things, we're able to build more complex things with more complex behavior. There's a lot of cases where I think conflict-free replicated data types might be interesting. Even if, let's say you're building this single source of truth web app, maybe someday you receive this requirement that we need to have a really complex offline mode, that you need to be able to do a whole lot of operations without having access to the internet. This could happen potentially depending on the types of things that you're dealing with. So then a conflict-free replicated data type could be a good solution to this. If your server and your client both are using the same conflict-free replicated data type, the client can just update as much as it wants to any of the information, and then when you have internet again, send that data to your server, and you're guaranteed that you're going to be able to perform that merge without having to do any conflict resolution. Another case that I think might be interesting for mobile developers is, imagine that you're just like an independent developer who just wants to build an app that has saves a document and doesn't need to have a backend to write and support, but maybe you want that document to be able to be synced in Dropbox or something. So even in that case, in the cloud computing world, it's really hard to make any app that doesn't have some necessity of having data moving on multiple devices just because your users buy new devices or things like that. So if you're worried about having to deal with those types of conflict resolution, if you were to represent your data as a conflict-free replicated data type and just serialize that as JSON and make that your file format, then at least you would know that there's not going to be a conflict when you want to move that data to another device. Another point. I've only started to talk about these things. This was more of an introduction to give you an intuitive understanding of the concept. But actually, if you want to go into this topic, it gets deeper and deeper. So among the stuff that I haven't talked about are operations like garbage collection. So one of the disadvantages of what we've seen so far is that those sets will continue to grow in size forever. Anything that gets added is always going to be in it. So is there any way that you can safely just start dropping things out of that set without having to worry about this property that it all converges? That's a more advanced topic, which some people have been able to do. Other stuff we haven't talked about are ordering things. So right now we don't have insert it in this particular point. We've been dealing with sets which are unordered. So there are more advanced techniques that build on these concepts that I haven't covered, but which you may be interested in depending on your application. And the second thing to realize is that while conflict-free replicated data types are guaranteed to provide a deterministic resolution, it might not be the one that you want. If we think about what if we just replace git merge, which everybody hates dealing with a conflict-free replicated data type? You could do that, but merging source code is kind of a tricky thing, and if it doesn't merge the way that you want it to merge, you might have problems like, oh, my source control subtly introduces bugs into my application while I am by merit of merging things, and debugging is actually probably worse than dealing with the merge conflicts. Trying to figure out when did this merge operation cause some bug to enter into our system. So there's a lot of cases. Some people have tried using conflict-free replicated data types for something like Google Docs, and some of them found that the way in which the text combined wasn't really what the users were expecting, stuff like that. So this is not necessarily guaranteed to be the catch-all solution for all conflict resolution. It may not be the one that you specifically need for your application. So that's something to keep in mind. But hopefully, you've been able to gain at least an intuitive understanding of this concept and maybe can start to imagine when it might be useful for your use case. Thank you. Any questions? Do we have time? Cool. I saw hands. Cool.
Hello. Thank you for this presentation. So I just have one question.
Yes.
Is there any well-known, simple, I guess, data type, conflict string that could solve the problem of edit? So for example, I have a string. Two or more clients can edit that string. So they have a copy of that data locally.